Hello class, and thank you for watching the second part to lesson 5.3, polynomial functions in the graph. In this lesson, we're going to be focusing on identifying the zeros of a polynomial functions and practicing our factoring skills along as determining the respective multiplicity of each zero. So let's begin by first defining what a zero is, and then we'll talk about their multiplicities. Now, recall that a zero is simply the value of x, or the x values in which f of x is equal to 0. So again, we call those zeros. Some places we also refer to these things as roots, or as the solution to the equation of f of x is equal to 0. So whatever x values that make the function equal to 0. Okay. Now, these roots of this polynomial equation on the graph, they appear as x-intercepts on the graph of this polynomial function. So if we were to graph these functions, we can find again these values, these x values, by finding and identifying where the polynomial function is going to cross the x-axis. Now let's discuss the multiplicity. The multiplicity of a zero is the number of times each factor equals to 0. So for example, if x minus c is a factor and it's being raised to the k power, this means that x equals to c is my 0. This is the value that will make this thing equal to the value of 0. And the multiplicity is going to be this number right there, k. The way to understand this and what this means is that what we're doing here in identifying the multiplicity is identifying how many times essentially x is going to equal to the opposite of this number that makes it equal to 0. Again, and this is referred to as the multiplicity. So let's take an example of this one right here. Okay, so let's find the zeros and their respective multiplicity. So to find the zeros, remember, we're trying to figure out this equation. When is f of x going to equal to 0? So if we get the function 3x, x minus 1 to the second power times x plus 5, when is this going to equal to 0? So by the zero product property, since again the product of these three values is equal to 0, then that means either 3x is equal to 0, or x minus 1 is equal to 0, or x plus 5 is equal to 0. And solving each individual factor set to 0 means that x is going to end up equaling 0, because all we have to do here, since we're multiplying by 3, is to divide by 3. This will require to move the 1 to this side, so in other words, add 1. So x will equal to positive 1. And the last one, we have to move the 5 over, so we'll subtract 5 from both sides, which means that x will end up equaling to negative 5. So here are the zeros of our function. So these three numbers will make f of x equal to 0. And again, you could just simply check now. If I plug in the number 0 into each one of these x's, the answer would be 0. Using, again, just any device, plug in the number 1. That's going to make the entire thing equal to 0. If I plug in the number negative 5 right there, this will be 0, and 0 times all of this stuff, again, will end up being 0. So, like I said, these are your zeros, your roots, the solution to the equation of f of x is equal to 0. Now, let's talk about the multiplicity. Well, to determine the multiplicity, we're going to look at each individual factor right here and see what power each factor is raised to. This first one right here is raised to the power of 1. So x equals to 0 has a multiplicity of 1. And the way I want you to understand this or think about this is that what this means is that x equals to this solution of 0 a total of 1 time. And what about x equals to positive 1? X equals to positive 1, since the factor is raised to the second power, that means that the multiplicity for x equals 1 is 2. And again, interpret this as understanding it, meaning to say that x equals positive 1 a total of 2 times. And the last solution was x equals negative 5. And what's the multiplicity on that one? Well, since the factor of x plus 5 was raised to the first power, that means that the multiplicity for this is going to be 1. So this again is the zeros and their respective multiplicities for each one of these situations there. All right, so If you look at the second example, same situation. We want to figure out what the zeros are and the respective multiplicity. So again, key idea is understanding again this. When is this thing going to be 0? Since it's already in factored form, finding what makes each individual factor, finding out what makes the polynomial equal to 0, since it's already in factored form, is equivalent to identifying what makes each individual factor equal to 0. So if I get each factor and set it equal to 0, again, ignoring the exponent in whatever the case is, like right here, this is just x, I can find the solution. And the reason I'm worried about this one, because again, remember, this right here just tells me how many times x is going to equal to 0. So here, x to the third power is going to equal to 0 a total of 3 times. So that one is already solved for us. So our multiplicity is 3. For the x plus 7, that requires that x be negative 7 in order for that to be 0. And the multiplicity for that one, since the factor is 1, since the x plus 7 is raised to the first power, means that the multiplicity is 1. And for the last one, since x minus 1 is equal to 0, that means that x would have to equal to positive 1. And your multiplicity would be the value of 3. So there is your zeros and their respective multiplicity. Now, for the rest of the examples, we're going to go over how to do the same thing, but practice our factorization skills, our quadratic trinomial situations, our greatest common factor technique, and things like that, just so we can review again those skills. But the overall idea is still the same. Now, we want to figure out, again, the values of x that are going to make this function equal to 0 and what the respective multiplicities are. So here, we have a polynomial function that is not in its factored form. So our first task is to do exactly that. And the examples, like I said, we're going to look at is going to start off by looking for the greatest common factor. So notice that we have 3 terms here. And normally when we have polynomials with 3 terms, usually they're quadratic, and we could break it up into the linear factors, x plus some constant, x plus or minus some other constant that give us this value here. But before we do that, we need to make sure that this degree up here, the highest is going to be 2. So we're going to look at every single term and see that every term has at most x to the second power. So we can factor out an x squared. So if I divide an x squared, we end up with x to the second minus 10x plus 25, and that is set equal to 0. Now, notice that your quadratic trinomial is found inside this parentheses there. So we can factor this into 2 factors, 2 linear factors. So breaking up the x squared to x and x, this sign right here is negative, and a negative times a positive is negative as well. So we're looking for factors of 25 that are going to add up to negative 10. So 1 and 25, 5 and 5. So 5 and 5 is the set that we're going to use here. Now, because these 2 factors are identical, I can write x minus 5 as x minus 5 to the second power instead of this x minus 5 times another x minus 5. So let's now identify the zeros. So our zeros are going to be what is going to make x equal to 0 and what's going to make x minus 5 equal to 0. And again, remember, we're ignoring the degrees for right now. So x equals to 0 is just 0, and because the exponent on that factor is 2, x equals 0 has a multiplicity of 2. And the next one, now moving on to the other one, x minus 5 is equal to 0. So x minus 5 is equal to 0. We're going to simply move the plus 5 to both sides, and x is equal to positive 5. So x is equal to positive 5. And what's the multiplicity for that one? Well, and that one, because the degree is 2, x minus 5 is raised to the second power. That means that the multiplicity is going to be 2. So there you have it. So again, we're doing the same thing. The only difference is that on these examples, you don't have the factored form that automatically tells you what the corresponding zeros are and their respective multiplicity. So we're going to work on the next examples. And the remaining examples, again, practicing our factoring technique by first looking at greatest common factor and then using our quadratic factoring technique, our trinomial quadratic factoring technique that looks like this. So moving on to this next example. So here, again, start the same way. We're going to figure out what is going to make f of x equal to 0. So we have x to the third minus 7x squared minus 18x. And you're going to notice that every single of the three terms has at least an x in it, x to the first power. So I factor out that x. We're going to yet again come up with, in one of the factors is going to be this quadratic trinomial, which we can now break apart using, again, our factoring technique, again, our linear factoring technique. So we're going to have a negative sign there. Negative times negative is positive. And the factors of 18 that are going to add up to a 7, with one being negative, one being positive, that's going to be 9 and 2. So a negative 9 and a positive 2 multiply to give us our 18. But then a negative 9 plus a positive 2 adds up to that negative 7 that we want to match up in the middle as our middle term. So now we have, again, three distinct zeros. X is equal to 0, x minus 9 is equal to 0, and x plus 2 is equal to 0. And you're going to notice that each one of these is being raised to the first power. So the multiplicity is going to be 1 on each one of them. So x is equal to 0 has a multiplicity of 1. X minus 9 is equal to 0 means that x equals to positive 9. And that is going to have a multiplicity of 1. And x plus 2 is equal to 0 means that x has to be negative 2 in order to make this. That number has to be negative 2 in order to make that equal to 0. And that's going to have also a multiplicity of 1. And again, and I'll just remind you here, what I want you to understand, what in terms of what this means, is that x is equal to 0 one time. X is equals 9 a total of 1 time, and x equals negative 2 a total of 1 time. And the reason that I bring this up is because I want you to focus again on the degree of our polynomial. Notice that the degree of this polynomial is 4. And if you look at the multiplicity again, the multiplicity adds up to that value there. This concept is going to be very, very important in the future when we talk about the fundamental theorem of algebra. The main idea again on this type of situations. So notice again that the degree of this thing is equal to 3, and the multiplicity adds up exactly to that value. If we look at already the factored form, if we look at examples 4a and b, remember how to get first of all, let me remind you how to get the degree when we have the factored form. So in the factored form of a polynomial, the degree is determined by simply adding up all of these exponents, which again correlate again to the multiplicity. So 1 plus 2 plus 1, that's a total of 4. So the degree of this thing is going to be 4, which again is what this adds up to. So if I can identify the multiplicity of each 0, I can also determine the degree of the polynomial. So here, since this adds up to a total of 7, the degree of this polynomial will end up being 7 as a result. So there's a direct correlation between the multiplicity and the degree. The total of the multiplicity, let me rephrase, there's a correlation between the total that the multiplicity adds up to and the degree of the polynomial function. So very, very neat. And like I said, this is going to be important in the future lessons. So let's look at some more examples. So okay, moving on to the next page. Here we have again this polynomial function. We want to see when it's going to make this equal to 0. And you'll notice again that there's a common factor of x to the second power here. So if I divide an x squared out of every single term, yet again, we're going to end up having a factor that's a quadratic trinomial. So breaking this apart into the two linear factors, negative times negative is positive. The factors of 30 that give me 5. Well, that's going to be a bit different signs. That's going to be 10 and 3. So x equals 0, x minus 10 equals 0, and x plus 3 equals 0. So x equals 0 is already solved, and because that's raised to the power of 2, the multiplicity is 2. X minus 10 equals 0 means that x would have to be positive 10, and the multiplicity for that would be 1. and x equals -3 is the last zero, and that multiplicity will also have to be 1, since that factor is raised to the first power, and again this one to the first power. And let's look at this again, the very cool interesting part here. These numbers add up to 4, which again is the degree of the polynomial. So if we move on to the second example, this example F, not the second example, but the next example, here the greatest common factor of x's, they all have at least an x to the third power, which is literally, I know the terminology is a little weird because we're looking for the greatest common factor, and the key word in that term is common. What do they all have in common? They all have a common at least an x to the third power. So we're not looking for the largest exponent, but the one that they have in common. So by doing that and factoring out that x cubed, we end up with the first term as x to the second plus 5x to the first and -14. And yet again, we have another quadratic trinomial. So factoring that into its linear factors, we end up with x plus, x minus, and factors of 14 to give us 5 are going to be 7 and 2. So x is equal to 0, x equals -7, and our third 0 is +2. And our multiplicity for x is equal to 0 is 3. The multiplicity for x equals -7 is 1. And the multiplicity for x equals 2 is also 1, which again, 2 plus 1 plus 1 is a total of 5. We're now moving on to a different type of example here. Notice that there are now 4 terms. So even if there was a common factor, we would not be able to use the quadratic trinomial factoring technique. And this requires, because of that, this requires a different technique. So in order to factor these type of problems here, when we have x cubed problem and there's 4 terms, is that we use a technique called grouping. So we're going to group the first 2 terms, x to the third power minus 3x to the second power, with parentheses. We're going to put a plus sign in between, and we're going to group the last 2 terms, -9x plus 27. And we're going to use here, in order to factor this, we're going to start by looking for the greatest common factor in each respective group. In the first group, you should see that the greatest common factor is going to be at least an x to the second power here. So you'll have an x to the third and you'll have an x to the second. Now, if they also have a constant, then you want to factor out that constant instead. Here, the greatest common factor in terms of coefficients is 1 and 3. Both of those numbers can be divided by 1. But I can also factor out, like I said, an x squared. That is always going to be true on this technique. So I can always factor an x to the second power. And I'm going to be left with x minus 3. So after finding the greatest common in the first term, finding the greatest common in the second term is going to be very, very easy, because we need to factor something so that we also end up with another x minus 3 in that second term when we factor out, yet again, the greatest common factor. And normally, for most cases, it's simply the leading coefficient. If this technique is going to work, and this technique of grouping works, then it's set up so after finding the greatest common factor in the first term, if you divide both of these terms by this leading coefficient, you should end up with x minus 3. The same thing as this here. If it doesn't work, and if you can't divide both of these numbers, then this technique doesn't work. But because again, we're scaffolding here and building up on this procedure, and everything on today's example is going to work the exact same way. So let's divide again and factor out that -9. So we're going to factor -9 from both terms. So that's how we end up with the x. Dividing out the 9 gives us the x. Dividing the 27 by this -9, factor out -9 from there is going to give us a -3. And you see, like I mentioned, these 2 factors in the parentheses should be identical. If they're not identical, check your arithmetic and make sure that they are identical. Okay, so now having done that, we're going to now use again the greatest common factor, because this is a term right here, and this is another term. We're going to factor out that common factor of x minus 3. So I'm going to factor out the x minus 3. So I'm going to factor this out, and what's going to be left in these 2 terms here is simply going to be the x squared term, and this term here plus negative 9, which is the same thing as minus 9. Okay, now we have to do one more factoring. This, because this is a what do you call this? A difference of squares. X squared minus 9 is the difference of squares. We can factor in using, again, our technique, our difference of squares technique. Recall that if we have a value to the second power and we're subtracting some other value to the second power, then we can break this up to, I'm going to write it underneath as a plus b and a minus b. Simply the square roots of both of these values. I take the square root of this, take the square root of that, which is going to give me a and b. And my factors are going to add those two terms and subtract those two terms. Again, the difference of squares. So here, that's exactly what we have here. 9 is 3 to the second power. So if I take the square root of x squared and the square root of 9, I break that apart and create x plus 3 and x minus 3. And since the idea behind all of this, and the reason we're doing all of this, is to figure out what's going to make this equal to 0. So from the first factor, x minus 3 equals to 0 because x equals positive 3. X plus 3 equals 0 means that x has to equal to negative 3 to get that to equal to 0. And x minus 3 equals to 0 means that x has to equal to 3 yet again. So our zeros are both positive 3 and negative 3. And what are their respective multiplicity? Well, positive 3, we have two of them. So x has a multiplicity of 3 2 times. X equals negative 3 only one time. So our multiplicity is 1. And there are the zeros and the respective multiplicities. So let's do another example similar to that one. So again, we want to figure out the zeros of this. When is this going to equal to 0? So we'll start by grouping again using our grouping technique. And you have to be able to recognize that this is the technique that you have to use, because we have, first of all, we have nx to the third power, and we have 1, 2, 3, 4 terms. So an even 2 and an even 2 in the two groups. In the first group, there will always be x to the second power as a factor, which gives us x plus 4. And like I mentioned in the previous example, make sure that the coefficients also have a common factor. And this example, that value is 1. Since dividing both 1 and 4 by 1 are going to give me 1 and 4, then again, the invisible 1 scenario thing we have there. So by getting x plus 4 in the factor as my factor in the parentheses, I should end up with the exact same thing. So all I need to do is divide both of these numbers by negative 16. Negative 16 divided by negative 16 is 1. And negative 64 divided by negative 16 is positive 4. So plus negative 16. So I factored out that negative 16 from both terms there. We're now going to factor out the x plus 4 from both of those terms. So I'm going to take that out of this big parentheses right here. Again, we have to assume that all of this is grouped together, okay? So we're going to factor this out, and we're going to be left with x squared plus negative 16, or just simply minus 16. And we're trying to figure out what that makes this equal to 0. So let's factor out one more time. Notice that this, again, is another difference of squares. So we have x plus 4, x minus 4. So what are our solutions? Well, x is going to equal to negative 4 because of this one. And x equals positive 4 because of that one. So our two zeros are simply positive and negative 4. The multiplicity for negative 4 is 2, while the multiplicity at positive 4 is 1. So let's step up the difficulty just one more level here. So in this example, again, we wanted to figure out what's going to make this thing equal to 0. And again, Notice that there we have an x to the third power, and there's 1, 2, 3, 4 terms. So we're going to use again the same technique by grouping. So we're going to group the first term with the second using parentheses. We're going to put our plus sign, and we're going to group the second and third term. So 243x minus 2187. So now in this example, notice that the leading coefficient of the x cubed is not a 1, it's a -3. So what I'm going to do, because it's not a 1, I'm going to look if I could divide this number by that -3, and I can. 27 can be divided by 3. That's going to give us 9, and we're going to divide the negative sign out as well. So we're going to factor out a 3 along with the usual x squared. So dividing that out, factoring that out, we're going to end up with x minus 9. Put our plus sign, and again, we should be able to find a common factor that leaves us with an x minus 9 as well when we find the greatest common factor among these two terms here. And like I mentioned before in the previous examples, if this technique works, then this is going to be true every single time. So if I just simply divide this number, divide both of these terms, by this number right here, by 243, I should end up with 1, obviously x, and this divided by 243 should give me -9. So let's check. And it does. I'm doing this again off camera, but this number divided by 243 does give us -9. So if I factor out 243, I end up with that value there. So we have x minus 9 and -3x squared plus 243. Now this does not look like a difference of squares, but I bet you anything that if I divide both of these terms by -3, trying to figure out what makes this equal to 0, and I divide both of these two things by -3, I will see a difference of squares in those terms. So let's factor out that -3. I have x minus 9. I'm going to divide the -3 out of the second term, so I'm going to put it right here in the front and factor that out. -3x squared divided by -3 is the x squared, and -243 divided by -3, that equals to a total of -81. And look at that, a difference of squares. So if I factor out our difference of squares here, this is going to break up to x plus 9 and x minus 9. And if we look at each individual factor, excluding this one doesn't count because it doesn't have an x. X minus 9 equals to 0 means that x has to equal to positive 9. X plus 9 equals to 0 means that x has to equal to a -9. And again, x minus 9 equals 0 means that x has to be a positive 9. So that means that the multiplicity of positive 9 is 2, and the multiplicity of -9 is 1. And this finally brings us to our final example for this video. And again, I want to do something very similar to the previous one, where we have a leading coefficient that is not going to be 1. Our technique does not change. Again, that's very important that you understand that you're just doing the same technique, seeing that you have this information, this type of polynomial, this is what you're going to try first. Like I was trying to say, now if this technique doesn't work, then we'll talk about what other options we have in lessons later on in this section. But for all the examples in today's homework, this technique will work every single time. So let's look at what we have here. So we're going to obviously factor out the x squared. That's always going to be true in the first group. And because we have a leading coefficient of 4, let's try dividing both of these numbers by 4. And it does. 20 can be divided by 4. So we can factor out a 4, which is going to give us x minus 5. Then you put my plus sign. Let me put my other grouping symbol. And I should automatically know I should end up with an x minus 5 as well. So if I divide both of these numbers by the negative 100, that's going to give me my 1x, and 500 divided by negative 100 is negative 5. So we're going to factor out the negative 100. Now since both of these terms have an x minus 5, we're going to factor the x minus 5 out. So we're going to be left with x squared minus 100. So look again, the scenario here, this 4 and 100 have a common factor of 4. So I factor out the 4, x minus 5 times x squared minus 25 is equal to 0. So using the difference of squares, we're going to write this as x squared plus 5 and x squared minus 5. So the complete factor form for this, which I didn't explain on the other ones, which you'll have to do for the homework, write the factor form of this, will be x minus 5 to the second power. Oh, and I made a mistake here in my notation. This is not to the x power, to the second power. This is just x plus 5. Okay, sorry about that. So we have x minus 5 to the second power. We have two of those. And we have x plus 5 to the first power. So this is the factored form of our function. This again is just the factored form of f of x. And now to figure out when is f of x going to equal to 0, we have our answers from the factor. So x equals to positive 5, a total of 2 times. And x equals negative 5, because we need a negative 5 here in order to make that equal to 0, only 1 time. And let me re-emphasize again that point on the homework. You'll be asked to write the factored form of each one of these polynomials. So for these examples here, make sure that you write the factor form like on this one. You don't write it like this, because this will be marked incorrect, because you have two x minus 9s. The proper way, in order to factor this, let me move this down, would be to write this as negative 3. So f of x will equal to negative 3 times x minus 9 to the second power, since you have two of those, times x plus 9. And the order of the factors doesn't matter. It doesn't matter if you write negative 3 first, this one second, and this one third. If you interchange these two, that's fine. But as long as you have this one to the second power. This again cannot go here, because you do not have two, obviously, you don't have two x plus 9s. So on that part of the homework, make sure that you write your answer, the factor form, using an exponent of 2 for any for the factor that's being repeated. Okay, because obviously, as you saw in these examples and the other ones, you're always going to end up with one factor having a multiplicity of 2, and 1 having a multiplicity of 1. And 2 plus 1, again, boils down back to this concept that we have this to the third power. Same as right here. 2 plus 1, because the degree of our polynomial is 3. So this concludes the second part of lesson 5.3. If you have any questions, again, message me. If you have questions on the homework, check out the videos again on the homework, or also click on message your instructor and send me an email through my Open Math as well. That's also an option. Like always, I appreciate you watching, and I hope you have a great day. Goodbye.